Next topic is remainder term in Lagrange's formula. Remainder term in Lagrange's formula. Remainder term, or you can say error term in Lagrange's formula. So, starting with suppose that Pnx is a polynomial in x of degree n. Then corresponding to a given function, assume that fx possesses continuous n plus 1 order derivative in the interval x0 to xn. Means that uh, Pnx is a polynomial and we can consider a function fx which have uh, n plus 1 order derivative, and if we differentiate it n plus 1 time, then we get the 0, and the values of x are x0, x1, x2 and xn. So approximating fx as a function of pnx and gx, so assume that fnx equal to pnx plus gx, then where gx is the same root as you have in pnx, that's x0, x1, x2 and xn. If x1, x2, xn are the roots of an equation, then you can find it uh, as you do in the quadratic equation. If alpha and beta are the roots of the equation, then equation can be formed by uh, taking some constant k and multiplying its factor x minus alpha and x minus beta. So for the known alpha and beta, you write the quadratic equation as x minus alpha into x minus beta, and in the same manner you can write here, if x0, x1, x2, xn are the roots of the equation, then gx can be written as kx, x minus x0, x minus x1, x minus x2 and x minus xn as if in the factorized form. Okay, now where kx is to be determined in the terms of fx, we need to find the value of kx in the terms of fx. So what we'll do to find out the error, we use a function phi t. Phi t can be written as ft, replace the x by t minus p and t, and the remaining terms. Replace every x by t and leave the roots x0, x1, x2. These are the constant values. So replace x by t and these are the constant roots of, yeah, or zeros of the polynomial x0, x1, x2 and xn. So we will not change these x0, x1 and x2 and xn. We keep this, and the so find out the error term. We define a function phi t, that is the difference of phi ft minus pnt minus kxt minus x0, and this equation can be formed. And phi t vanishes at n plus 2 points, means that if you differentiate it, it is a function in t, so if you differentiate it 2 and n plus 2 times, then its derivative becomes 0. The points of the differentiation will be here x, x0, x1, x2 and xn. So count that, keeping x 1 point, count it 1, x0 2, and from x1 to xn total points is n points. So total overall, these 2 points x, x0, this is x and x0, 2 points, and this is n points. So overall n plus 2 points. So if you differentiate this equation n plus 2 times, you will get the derivative 0. So one theorem we have studied in the class 10th or 11th level, that is the Roll theorem. Then differentiating this equation with respect to t n plus 1 times and applying Roll theorem. What was the Roll theorem? That if a function is differentiable and continuous in the interval ab and fa equal to fb, then there exists a point t or c for which the derivative of the function becomes 0. So here this function possesses n plus 2 continuous derivative, and n plus 2 2th order derivative is 0. So we will differentiate it for x naught, x1, x2 and xn, not for x only. Okay, so we differentiate only for n plus 1 times, and phi t has a real root in the interval x naught to xn, so differentiate it n plus 1 times and apply the Rolle's theorem. We get, now next topic is remainder term in the Newton's forward formula. For the Newton forward formula, we make substitution as x minus x0 upon h, where the value of x are equally spaced. Spacing is taken by h. X1 equal to x naught plus h, x2 equal to x1 plus h. In that way, x minus x0 is equal to, what we'll get here, x minus x0 equal to hu, x minus x1. So put the value of x1 here, x naught plus h, x minus x naught minus h, x minus x naught, yeah, this will become hu minus h, so hu minus 1. In the same way, you can get x minus x2 equal to hu minus 2, and x minus x3 equal to hu minus 3, and x minus xn equal to hu minus n. Putting this value of x minus x0, x minus x1 and x minus xn in the remainder term as in the Lagrange's formula. We have obtained the remainder term in Lagrange's formula. First we will proceed just like the remainder term found in the Lagrange's formula. Then we apply this substitution for the Newton forward formula, and finally find the value of Rn, that is the remainder term, as in the Lagrange's formula. So this will give you the remainder term or error term in the Newton forward formula only because. And next topic, Newton's backward formula. So first derive the Lagrange's formula if it comes in the examination, then B, make substitution as in the Newton's backward formula. U equal to x minus x no, xn upon h, then x minus xn equal to hu, x minus xn minus 1 equal to hu plus 1, and so we can get x minus x naught equal to hu plus n. So these values will be put in the remainder term as obtained in the Lagrange's formula by making the substitution like the Newton's backward formula. We get the remainder term here, h ki power n plus 1, f to the power n plus 1 upon factorial n plus 1, f fn plus 1 xi lies between x naught and xn, u plus 1, u plus 2 and u plus n. This is the remainder term in the Lagrange Newton's backward formula.